Hey everyone, chapter 15 now. We're gonna take a trip back to Vectorville and learn some things about these, I guess you could call them functions called vector fields. So basically a vector field, basically a vector field takes the inputs of points x, y, z, or just x, y if you're looking in a plane, and it assigns a vector to every single point that you can plug X, Y, and Z in for, right? So if we were to graph that, typically you wouldn't graph the entire vector field because, well, it's a lot, right? But a lot of computer programs can come up with vector fields, and a lot of times you don't really need a lot of the in-between points to get an idea of where something is going. So vector fields are going to look a lot like vector valued functions that we talked about way back in chapter 11. Um, Difference here is that when we did vector valued functions in chapter 11, all of our variables were parameterized. So everything in the vector equation that we were given was in terms of just one variable t. Now that we know how to work with functions that have two and three variables, vector fields that we're going to see are going to depend on x, y, and z rather than just a parameter t. Um, in addition to that, I wanted to talk about some commonly encountered examples, especially because we get people from all sorts of different majors in this class. So one that most of us will see are velocity fields. And a common example of that is when you're watching the Weather Channel or looking at your weather app and you look at, say, the wind, right? A lot of times you'll see all these arrows pointing in a certain direction, maybe of varying lengths, but a lot of times they use color to describe magnitude. But the point is the speed and direction of the wind, i.e. the velocity of the wind, is represented on those plots. And that is an example of a vector field. Because for every point on the map that they have, they're assigning a vector, i.e. the velocity of the wind at each point. Um, some commonly encountered ones in physics that we see are gravitational and electric fields. So these formulas that you learn when you take your introductory physics courses really just give us a multiplier for a vector, right? So whatever this is, we multiply by the component or by each component in the vector r, which here is made into a unit vector, right? So basically, for any value of x, y, and z in the vector r, right? We have a vector assigned to each point. And one thing that you'll notice about gravitational and electric fields, and maybe even see some memes about this, oh, that square should be outside, not inside. Yeah, is that these constants that we're multiplying the unit vector in the direction of r by look very similar to each other, right? You have some kind of constant multiplied by two quantities, right? For gravitational fields, that would be mass. For electric fields, it's charge. Um, and in both cases, we're dividing by the magnitude of the vector r squared. So because they have the same kind of shape, a lot of times we'll refer to these as inverse square fields, right? Because this factor we're dividing by the magnitude of vector r squared. And they actually have, well, I'm actually going to talk a little bit more about these guys later, right? In the meantime, let's look at an example where we sketch some vectors in a velocity field. Right, so velocity field again is a type of vector field. And notice here that for this vector field, there's only a k component. So we'll start off by just graphing what the surface would look like. So if you remember when we talked about the graphs of functions of two variables, this is going to end up making a paraboloid. And you can think of the base of this paraboloid as a circle, which is drawn a little off to kind of give the illusion of a third dimension, since I'm drawing this on a paper. Yeah. All right, and then another thing I want to remind you of are the level curves that we talked about back in chapter 13. Yep. All right, so basically if I were to take this this little circular piece of that paraboloid and project it downward, right, that makes a level curve because all the points on this line have the same z value, right? Level curve, contour line, whatever you want to call it. And I'm drawing those because I'm going to illustrate something when we actually plot some of the vectors. So if I were to draw this, let's say that I plug in 0 for x and for y, right? So 0, 0, 0. The vector that I get would end up being 16k. And because of what we know about the graph for 16 minus x squared minus y squared, we know that the z coordinate at the very top of the paraboloid is 16. So basically this vector from the origin points that way. All right, what if we plugged in 1, 1? Then I would get 14. So I would go over 1 on the x direction, 1 on the y direction. And then I would end up getting a vector that points directly up and goes 14 units, which is going to be a point on that surface. And I can do this with all sorts of things. Like if I plug in 1, 0, right, 1 for the x, 0 for the y, I end up getting 15. So it would go slightly higher than this guy, but not quite as high as the one we drew at the origin. Right, so when we draw all of these vectors, they end up terminating on a point that's on that surface. And one interesting thing about this vector field in particular is that all of the vectors that we drew, and really all the vectors that are in this vector field at all, are orthogonal to the level curves. And that should sound familiar because that's the definition of something. Yep. It's a property of the gradient, right? Remember, when we calculate the gradient is always orthogonal to level curves in a three-dimensional space. And and that actually leads me into the next topic here. So here we notice that all vectors are perpendicular or orthogonal to the level curves. What this implies is that the vector field F that we just drew is the gradient of something. And we have a vocabulary word that's new to this chapter that kind of describes this situation. Specifically, we would say because f is the gradient of something, that f is a conservative vector field. Okay, conservative vector field. Now, when you see that word, conservative has nothing to do with the vector field's political views. We say conservative because it kind of goes back to those inverse square fields that we talked about and a law called the conservation of energy. Basically, in terms of vector fields and stuff that we've discussed in this course, inverse square fields are conservative, and a result of that is that their energy is conserved, right? Meaning that the kinetic plus the potential energy experienced in these two field or at any point in this kind of field is constant throughout the field. Right. So remember, your kinetic energy is due to actual motion. Potential energy is the energy that's there because of where a point is in the vector field. And think about that one. It's kind of like if I have a point that is placed somewhere where the gradient is a lot stronger, right? The potential energy would be higher than if I'm at a place where the gradient has a pretty low magnitude. Like even if you think about it in terms of wind, right? If you're at the top of a windy hill, you're in a place where the gradient is stronger. If you're sitting in Houston traffic and there's no breeze and you're sweating miserably, then that's very little potential energy. Right, so just some thoughts there. So a conservative vector field is a vector field where f is the gradient of something. Right, and we actually have two different ways to, yeah, we actually have two different ways to test whether or not a vector field is conservative, depending on how many dimensions there are. So if I look at a two-dimensional vector field, one way that I can test if a vector field is conservative, is I can look at the partial derivatives of the components and see if they're equal to each other. So let's say that I have some vector field in two variables. All right, we know that there's going to be an I component that is a function of x and y. There's going to be a j component that is a different function of x and y. All right, and basically if I take the partial of my I component with respect to y, and I take the partial of my j component with respect to x, if those two things turn out to be equal for all values of x and y, then that implies that f is conservative. And let's break this down a little bit. Why are these derivatives important? Because let's think about something. If f is conservative, remember, what does that mean? That means that f is the gradient of some other function. And if f is the gradient, remember that means that m and n are already first partial derivatives of whatever function f is the gradient of. So if these guys are already first derivatives and we take, because remember, this would imply that if little f, so let's say that little f, let's make a definition here. So I'm gonna should let little f, so del little f be equal to capital F vector. All right, basically we're saying that the vector field F is the gradient of little f. By the way, this does have a name. This is called a potential function. That is not how I spell a function. All right, so what this notation tells me is that m is the first partial derivative of little f with respect to x, and that n is the partial derivative of little f with respect to y. Right? So if I were to take these derivatives, right? So if I take the derivative of m with respect to y, essentially that's giving me fxy, mixed second partial derivative. And similarly, if I do the partial of n with respect to x, then this is giving me fyx. So to show that f is the gradient of something, we're using the fact that f is a gradient, right, to compute second partial derivatives. If they're the same, then we say f is conservative. And remember, the second partial derivatives, fxy and fyx, are the same for any two variable function as long as that function is continuous. So, so basically, you're just checking to see if the second partials are equivalent, right? Given the first partials. That's all it is. Let's look at an example with a two-dimensional vector field. So let's say we have f of xy. So this is our vector field. Is equal to x squared y I plus xyj. All right, and we want to determine if f is a conservative vector field. So first off, remember this tells me that the partial derivative of the potential function f with respect to x is equal to x squared y. And this tells me that the partial derivative of potential function f with respect to y is equal to xy. So if I take my second partial, right, fxy, I'm going to start with fx and take the derivative with respect to y. This would give me x squared. Now, if I do the same and I look at fyx, right, I have my partial with respect to y. If I differentiate this with respect to x, I get y. These are not the same thing. Right? While they may be equal, or while they may be equal for certain values of x and y, this is not true for every value of x and y. That tells me that f is not conservative. Might mean that f is a liberal. But anyway, so f is not a conservative vector field. There's not really a word that we have for that. All right, but let's look at another example. Let's say in this case, we have the vector field f in the plane is equal to 2xi plus yj. All right, so again, you can write it out like this if you kind of need that visual, right? But you can also just say, all right, I'm going to take the partial with respect to y of my x component. For that, I get 0. And then I'm going to take the partial with respect to x of my y component. That's that guy. And with that, I get 0, right? Since these two partial derivatives are equivalent, that implies that the vector field F is conservative. All right. So another cool thing to look at before we talk about three-dimensional vector spaces is this potential function that I've talked about. So remember, conservative vector field means that capital F, the vector, is the gradient of some function, little f, the potential. We can actually find the potential function relatively easily, right? Because we know how to do backwards derivatives, right? That's just integrals. So, for example, let's say that we have our vector field f of xy is equal to 2xyi plus x squared minus yj. So first thing, before I go about trying to find a potential function, I should probably look at this and make sure that there actually is a potential function. Meaning I'm going to check and see if f is conservative. Because remember, if f is not conservative, then it wouldn't make sense to try to find a potential function, because that would mean that f is not the gradient of anything. So with that in mind, I'm just going to check. If I take the derivative with respect to x of my x component, 2xy, I end up getting 2y. If I take the derivative with respect to y of my y component, wait, hold up. Dude, I did that backwards. My bad, y'all. So the partial with respect to y of your x component. This is why it makes sense to write it out the way I did the first time. But anyway, if I take this derivative, that actually gives me 2x, not 2y. 2x, okay. And then here we're taking the partial with respect to x of the y component. Yep. So it should always be opposites. If I take the derivative with respect to y, that is of the x component. If I take the derivative with respect to x, that is of the y component. So with that said, right, this is going to end up giving me 2x as well. Because my x and y components are the same, or since these derivatives are the same, that tells me that f is conservative, vector arrow. And the reason I needed to check that is because now I know that there actually is a potential function. Because here's the thing, if you don't check that and it turns out that f is not conservative, you're gonna, well, it's gonna get pretty rough for you pretty quick. But now that I know that f is conservative, I know that there's gonna be a potential function, and I can kind of, yeah, and I can kind of use the fact that f is the gradient of something now to figure that out. So we know because f is the gradient, that the partial with respect to x of our potential function f ended up giving us 2xy. That's why it was the I component. And then the partial of f, little f, potential function with respect to y ended up giving us x squared minus y, and that's how it became the j component. So if I want to find f, then I need to integrate each of these partial derivatives with respect to the same variable. So I'm going to start by integrating 2xy with respect to x. If I do that, I end up getting x squared y. And instead of writing plus c, I'm going to write plus g of y, right? Because this could be any function of y. Remember, if I take the derivative with respect to x of something that only involves constants and y's, then that would zero out. So x squared y plus something that might involve y. Now, if I take the integral of the y component, x squared minus y dy, then I end up getting x squared y from the first term minus y squared over 2 plus some function that might involve x. But since I already took the derivative with the integral with respect to x, this is the only involvement that I'll get from x. Right? When I take the integral with respect to y, this is all the involvement that I'll get from y. Now that I know what these different pieces are, I know that my potential function f is equal to x squared y, that was the term that popped up in both of them, minus y squared over 2, and there might still be like a constant that would go away with either, or with differentiation with respect to either variable. For that, we can write plus, maybe write plus c. Your textbook uses k, but old habits, y'all. All right, so this ends up giving me my potential function. And if I vary the value of c, I get an example of a family of functions that all have the same gradient. Pretty fun stuff. So now that we've found a potential function, we've been able to test if a plane vector field is conservative. Let's look at space vector fields. So vector fields in 3 dimensions that involve x, y, and z. All right, so for us to be able to test whether or not a 3-dimensional vector field is conservative, we're going to need to learn about something called a curl, not a bicep curl, but just curl of a vector field. And this will have a lot more significance in later parts of this chapter, right? And if you ever have to take a thermo course, then yeah, you'll see this a lot because it's involved a lot in Maxwell's equations. Yeah, but even if you take other things like fluid mechanics or electrodynamics, any of that stuff, you'll see this in some capacity. Before I talk about curl, though, I want to bring up this guy, del. So we've only seen this in one context so far, namely that this is the symbol that we use to take the gradient of whatever function comes after it. When we learn about curl and another thing called divergence that I'll also talk about in this video, you'll see this used in kind of a different way. So this is an example of what we would call a differential operator. And basically, operators are things that act on functions or expressions, right? For example, a dot, like the dot and the dot product, is something that inputs two vectors, and output's a scalar, right? Differential operator, you input a function, you get out a gradient. And the way that we're going to see this is a little different notationally than what you're used to, right? But honestly, moving forward, it's something that you should get used to, right? Because when you study any kind of hard science, like everything basically revolves around operators. Like when I was in grad school, my specialty was quantum mechanics, and literally everything in there was operators, partial differential equations. Yeah, that's a thing. And I mean, when you learn any application of physics, this comes up because physics is applied math. Anyway, so it's a differential operator, and we'll see it in different contexts. When we talk about the curl of a vector field, all right, we can determine that by taking a 3 by 3 determinant. It's basically a cross product. So before I write out what the determinant looks like, this is how you'll see curl written in basically any other textbook. Even in our textbook, they use this notation. So it's the cross product, del cross F. Okay. And here, del isn't acting on anything. We're not taking a gradient and then doing a cross product. We're using this differential operator and taking the cross product of that with a vector field F. And again, before I write out the actual matrix for this, if I wanted to write this in vector form, a component form, I should say, notice that this is going to be, so your del differential operator looks like this if I write it in component form. And we're taking the cross product of that with this vector field. All right. So if I go to write out my determinant for cross product, remember your first row are going to be the unit vectors I, j, and k. Your second row is going to be the first thing. So that's going to be our differential operator. And a notational thing here, it does not make sense to write that as fx, fy, fz. Because if you do that, then that's assuming that you already used this operator on a function f. So when you're writing this out, you should stick to using this notation, right? Because any other notation that you find will already assume a function whose gradient we found. And here we're looking at this, assuming that it's a conservative vector field. All right, so basically if I evaluate that determinant, then I'll find the curl of F. And our test for three-dimensional vectors or vector field is if the curl of F, could also write that as a vector as well. So if the curl of F is equal to 0, 0 vector, that implies that F, the vector field, is conservative. So if your curl is the 0 vector, then the vector field F is conservative. Now, because this is going to, because this is a thing that people kind of, I'm not going to say people struggle with curl and divergence, but a lot of times, especially if you go a while without using it, you can confuse curl and divergence. And one thing that I did tell you guys at the beginning of the course is that when we're doing anything involving vectors, it's very important for us to go through and figure out if the result we're getting should be a vector or a scalar. All right. And remember, this is a cross product, and the result of any cross product is a vector. So in your notes, I do want you to write, and I want you to make it attention grabbing and crazy colors. Things that will make the conservative vector fields look at you in disappointment. I want you to write out that curl is a vector. Curl is a vector. It's a cross product, so it is a vector. When we talk about divergence in a little bit, you'll find that divergence is a scalar. And so curl is a vector, cross product, curl, cross, they both start with C. And divergence is a scalar. Divergence dot, they both start with D. It's not cool. Didn't even make that connection until literally just now. Okay. So let's use this in the context of another example. So I'm comfortable here. All right, so for this example, we're going to look at the vector field F equal to 2xyi plus x squared plus z squared j plus 2yz k. All right, so this is our vector field. We want to figure out, we want to figure out if vector field F is conservative. So we're going to look for the curl of F, which you can also denote as curl F. And we know we need the determinant of a 3x3 matrix, where the first row is our unit vectors ijk. The second row is our differential operator, d, or partial with respect to x, partial with respect to y, partial with respect to z. And the bottom row is going to be the components of the vector field F. So we get 2xy, x squared plus z squared, and 2yz. Okay. So remember how this works. If I take out the first row, first column, the intersection is I, and I take the determinant of this matrix. Now, when we multiply this out, right, you're taking an operator times a thing. Basically, that just means that this operator will act on this thing. So that first part, or actually, yeah. So that first part, we're going to have the partial with respect to y of 2yz. And we're going to subtract from that the partial with respect to z of x squared plus z squared. Right, and that's going to be our I component. Now the j component, remember you have to subtract the j, you subtract the even columns. So if we have 4 dimensions, the next one would also be minus. So plus, minus, plus, minus, plus, minus, ad nauseum. Okay, and then if I take out that second column, first row, I'm doing this determinant. So partial with respect to x of 2yz minus partial with respect to z of 2xy. And lastly, if I cover up third column or first row, third column, we're taking that determinant. So we have partial with respect to x of x squared plus z squared minus partial with respect to y of 2xy. Okay, so now if I look at this, partial with respect to y of 2yz, that's going to give me 2z. Partial with respect to z of this guy is going to give me 2z. And for my j component, partial with respect to x of that is 0 because there's no x in 2yz. Partial with respect to z of 2xy is also 0 because there's no z in 2xy. Now for the k component, this derivative will be 2x, and this derivative will also be 2x. So notice in each of these cases, our x, our y, and our z components all end up being 0, which means that the curl of this vector field f is equal to 0, the 0 vector, right? That's 0, 0, 0, 0 I, 0 j, 0 k. Because the curl of f is equal to 0, we know that f is conservative. All right. And your textbook also talks about a term called irrotational. Yeah, that has to do with kind of an interpretation of what curl is that we're going to talk about in a different section. So if f is conservative, we can also say that f is irrotational. I'm only going to say that in case you are asked about that in your homework. Okay. So just like we can determine whether f is conservative for three-dimensional vector field, we can also look to see what the potential function would be, basically in the same way. Like if I have, yep. So if I have the exact same vector field that we just looked at, so we have 2xyi and x squared plus z squared j and 2yzk. All right, we can look for little f, the potential function of that vector field. So first thing I want to preface this with is just like when we talked about the two-dimensional version, it's important for us to check and make sure that the vector field we want our potential for is actually conservative. Because remember, if it's not conservative, then it doesn't make sense to find a potential function because this wouldn't be the gradient of anything. And another thing I do want to say, just to kind of relate this back to the two-dimensional case. We look at the curl, we figure out if it's 0. Remember, this can only be 0 if all of the corresponding mixed partial second derivatives are equal to each other. So for example, basically for the I component to be 0, for the I component to be 0, the partial with respect to, yeah, basically fxy and fx, or this is going to be fxy minus fyz. Oh, yeah. Yeah, I don't know where I was going with that. But anyway, for the curl to be 0, a bunch of these mixed partial derivatives actually have to be equal to each other, right? Like you see, these two second partial derivatives were each 2z. These two were each 2x. These two were each 0. So because of that equality amongst the mixed second partial derivatives, F turned out to be a conservative vector field, right? In the same way that in 2 dimensions, we only had 2 different mixed partials we could have, right? Fxy and Fyx. Okay. All right. So anyway, if I want to find the potential function, as I mentioned before, it's going to work pretty similar to the 2-dimensional case, where we're taking the integral with respect to the appropriate variable for each component. So I would take the integral of 2xy with respect to x, because that's my I component. I would get x squared y as my antiderivative, and I know that whatever the leftover is, it can involve y, it can involve z, it can involve functions. Or constants. Okay, and then similar thing with my j component. I can take the integral with respect to y. So for that first term, I would get x squared y. For that second term, I would get yz squared. And then whatever my leftover function is can involve x and z. And then if I take the integral of my k component to yz with respect to z, all right, I'm going to end up getting yz squared. And whatever's left over can involve x and y. So if I look at these 3 results, I get all of the different terms that are in my potential function. So I get that my potential function little f of x, y, and z is going to be equal to x squared y plus yz squared plus a constant c. And there we go. That's the potential function. That's how you find it. Bing, bang, boom. All right, now one last topic for this video, section 15.1 in your textbook. We're going to talk about divergence now. So conceptually, your divergence is essentially a rate of flow within a vector field. So like if I take a tiny little cubic space at any point in a 3-dimensional vector field, the divergence tells me the rate at which points in that vector field are passing through it. All right, so it's almost like the slope of a tangent line, but for a vector field. All right, so this one, divergence is a scalar. And the divergence, which we denote as div of a vector field f, is equal to our differential operator del dot vector field f. So this time, instead of taking a cross product, we're taking a dot product. So cross product for curl, they both start with C. And remember the result for that is a vector. Dot product for divergence, they both start with D. Remember the result is a scalar, right? So this is like the slope of a tangent line, but in a vector field. It's the rate at which points or particles or whatever flow through a specific point on a vector field. Yeah. So again, just to remind you, our differential operator written out as a vector in component form looks like this. And we're taking the dot product of that with these. Okay. So that's how you compute divergence. There's not really a requirement on a vector field being conservative for this to make sense. Like you can use this for any vector field, right? But if we get the case where the divergence of f is 0, and that's scalar 0, not vector 0, then that means that f is divergence free at that point. Because remember, your divergence, you can write your divergence out as a function of x and y and z, right? Just know that if you were to plug in an x, y, z to that function, you would get the divergence at a point, right? Similar to how just taking the first derivative gives you a formula for the slope of the tangent line. So let's look at an example where we take the divergence of a vector field F. All right, so the divergence is going to be our differential operator, which I'll write in component form just to illustrate the idea. Dot, and then F. Okay. So remember how your dot products work if you have vectors written in component form, right? It's just first component times first component plus second component times second plus third times third, right? So this one, my divergence would be the partial with respect to x of x cubed y squared z plus partial with respect to y of x squared z plus partial with respect to z of x squared y. Then if I look at that first term, partial with respect to x would be 3x squared y squared z. Second term, there's no y there, so that would be 0. Third term, there's no z there, that would be 0. So our divergence in terms of x, y, and z is 3x squared y squared z. Right? So if I plug in any value of x, y, and z, i.e. a point, I can get the divergence at that point. So if I wanted to find the divergence of f specifically at the point 2, 1, -1, I would just need to plug those values in. So we get 3 times 2 squared times 1 squared times -1, and the result I get is -12. So at that point, the divergence is -12. And here's another thing, just because again, I want to give you guys some insight to other fields of study. Right, there are different words for divergence free, depending on field of study. So for example, yeah. So for example, if you ever have to study fluid mechanics, you might look at a velocity field of a fluid, right? And if that velocity field is divergence free at a point, then we would say that that fluid is incompressible at that point. Similarly, if you are studying E&M, right? If you have a vector field of, say, electric potential that's divergence free at a point, we would say that that's solenoidal, like a solenoid. Makes you wonder how it got its name. Anyway, that was our introduction to vector fields, curl, and divergence, and the idea of what a conservative vector field is. So yeah, that's the end of this video. Happy mathing.